Okay, guys. So what I'm going to do, I'm just going to get into some of the concepts. I'm going to go right out of the textbook, chapter 2, fundamental concepts in understanding bioenergy and bio-based products. And just as a little side note, yesterday I was driving around with 3 or 4 gentlemen who've been in the biomass industry in Montana for quite some time. One's Patrick Brown with International Biomass. He makes this thing he calls a tiger pellet. So he's got 90% wood, 10% plastic resin. This is shippable in the same manner you could coal. So it's all of the beetle kill, it's the junk, it's whatever's in the tree, along with our friend the plastic bag. You combine those 2 bits of garbage together, and it's becomes energy. I was also running around with another guy by the name of Bob Vanderbyle, who's working with the company PCS Biofuels out of Canada. They're about to go gangbusters. They're actually mining landfills right now and making commercially pure carbon. So that will go, so that'll go into, the steel, and here's some chunks of it too. Here's the, steel and, what's that?
This is landfill.
Yeah. Mm-hmm. Awesome. Or out of the agricultural waste. So they're squeezing water out of it, they're squeezing cellulose out of it, and at the end of the day, you just got elemental carbon.
The heat and pressure.
You actually use this like filter water?
Yep. So lots of uses for it.
Poison, you can do all kinds of stuff.
It's got a little burn smell to it, or
Sometimes.
yeah. So
I don't know if anybody else is working.
So this stuff is for real. I mean, this isn't just kind of like this is happening right now in Canada, in Montana, and it's sort of the next generation, if you will, for the woody biomass industry. I've got another guy who has a real passion for the forest and for sustainability, and would like also to take a lot of these slash piles that used to be, the teepee burner thing, let's just waste it and destroy the atmosphere, take that material and turn it into a biofilter. So the woody biomass is actually acting as a filter. So just yesterday, drove to Butte to discuss how to commercialize some of these technologies. Helena to discuss commercializing them with the MBRCT, so Montana Board of Research and Commercialization Technology. And then just after that, we were at the Mansfield Center in Butte. And what I'd like to do, maybe for 244, but certainly for 214, is get you guys down there. It's just this giant power system. In fact, they've got they spend $10,000 a month on electricity, and they can't account for like $2,000 worth of it. And so, so they've got several people sub-metered. They've got their meter, and they're looking at a $10,000 bill, but they're looking at all these others, and the numbers don't add up. So I might send the 214 students down there on a little. So there's a lot of pretty cool energy tech. The Head Frame Spirits is in there. I know they're using some juice too.
That place is classy.
Yeah. So they're making a lot of their own distillation equipment there. Okay, so that's just kind of recapping what I'm doing in bioenergy and energy storage and distribution in Montana. So let's look at the textbook. I'll give myself.
You guys got to remind me that it's recording.
Yeah, it's okay. It's all right. It's all right. We'll see who's listening, won't we?
Yeah, you will. My mother used to tell me I was the most uncouth person she ever met.
Well, whose fault is that, Mom? Oh, gosh. All right. So, 244, week 2, chapter 2. So, fundamental concepts in understanding bioenergy and bio-based products. So starts right off, 2.1s with the introduction. There's some chemistry involved. The next section there is engineering thermodynamics. And then finally there's mass balances. So I'm just going to dig right into mass balances. And for me, mass balance goes hand in hand with energy balance. First law of thermodynamics, you can't create or destroy energy. So that's really all we're doing right here. It's just kind of writing down the first law of thermodynamics. So I'll just write it the exact same way that we see it in the book. So here's dm CV, so the subscript on that is CV, dt equals the sum, and so this is it's a sigma, and it means summation. It's different from this summation symbol. This is the integral sign, so this is continuous summation. Summation, and the sigma is a discrete summation. So what's that mean? Well, the easiest way I like to think about it is like, you know, apples. So let's say we got a bunch of apples here. Kind of look like hearts, maybe bombs, maybe both. Valentine's Day is coming up. No, they're apples. But you're going to add, you know, 1 apple plus 1 apple equals 2 apples. You know, so that's kind of your discrete summation, right? So the 1 plus 1 equals 2. Continuous summation, I guess I think more of think of as water. So let's just think of Niagara Falls for a second. You've got the you know, the Canadian Falls coming over here, the American Falls are over here. Together, they're going to, you know, flow down into this pool and then out through the St. Lawrence River, right? So here's the American, here's the Canadian, and then what you know is that in water, you're not keeping track of every single water molecule or fish or guy in a barrel, whatever. You're just like adding up all that mass. So that's the difference between continuous summation and discrete. Does that kind of make sense? Well, here, let me just...
Didn't you add up all the matter in discrete also?
I did. Here's another way to just like tie it in with your everyday language is my son will come home from school and say, "Dad, there were less people in my class today than there were yesterday." And I say, "Well, don't you mean fewer people?" Because less actually means something that's continuous. You would say there's less heat in the room. But for people, like you count them up, 1, 2, 3, 4, 5. Fewer means something that's discrete, whereas less means something that's continuous. So
like objects versus like, you know, air or large bodies of something like water or air, or is that what you mean? Or?
yeah, I guess what I mean is you know, something that's discrete. Like I've got two jars in my hand, and I would say you know, 1 plus 1 is 2. You can sort of count them. But in terms of water going over Niagara Falls, or you know, snowfall or something like that that's just kind of always happening, you think of it as a continuous process rather than one at a time.
That makes more sense.
Something that's always adding in and going out continually versus like this is an object made.
Yeah.
Temperature.
Temperature, yeah, you would think of that typically as a continuous variable versus, yeah, so that's, not to confuse it, but we see that every day in life too, like, you know, counting things versus just,
It's there.
it's there, yeah, and you gotta add it up somehow, but, okay, so hopefully that clears up what this funky, and the way I think about it is that this sigma, this uppercase sigma, has corners on it that you can count, and this integral sign does not. So it's kind of always flowing, whereas the sigma. So that's how I kind of remember the difference between the two mnemonically. Okay, now we're going to put a little I down here, and we're going to put an M here. I'm going to stick a dot right there, and I'm going to put another I right there, and then another negative sign, summation.
Is it like M dot subscript?
Subscript, yeah, that I is a subscript. And here's another M dot, and here's another subscript. Now let's just read through here.
The I and E are exit, correct?
Yeah, I you can think of as internal, like incoming, and E you can think of exit or outgoing. Yeah, exiting. Yeah. And what I'll do, I'll take this sort of, and you can just think of this as a compact notation, and really all it is, it's just addition. That's all it is. Well, with a little bit of division. Okay, so let's take that, get on to the next figure. Okay, so here's the mass of the control volume, and just to get us thinking, like this box that I just drew could actually be the office we're sitting in right now, and these masses coming in. So here's M. Well, I'll just copy just how he's got it in the book. So here's M, I1 dot with an arrow coming in. Let's see, I've got MI2 dot coming in over here. This is MI3. So I'm just copying straight out of the textbook at this point. But if you want to get some practice drawing it, so this is pretty convenient because what we could think of each of these three masses is just each one of the three students in the room walking into it. You know, each one of you has a weight. If there was a scale under the floor, we could add them up, and that's what the mass of the room would be. What are these other guys? Well, I guess he goes all the way up to 5 masses. I won't draw those. Let me just draw the other 3. But let's just say maybe there were other people in the room previously. So this is going to be M exiting 1. Here's going to be M exiting 2. And here's going to be M exiting 3. Now, these we could think of these in a couple different ways. One would just be when the 3 students in the room leave, we'll be back to the original mass. We could also, it could be some other mass. You know, if I took this water bottle and chucked it out of the room, that could be the exiting mass 1. Take this one, throw it out of the room, that's exiting mass 2. Take this one, that's exiting mass 3. So all we're doing is accounting for mass. And the reason for using this unique looking symbol, the sigma, is that you might have hundreds or millions or as many as you can count masses. You know, these could be logs flowing in and out of a lumber mill. This could be logs going into a chipper and chips flying out the other end. So this is just the way to keep track of mass. It's just mass accounting. So let's take that first equation and we can write it out one more time. like so. And let's just do one hard example so that the funny symbols that we're seeing on the screen actually make sense with the example of us just sitting in the room. So let's do it this way. So I'm just going to say mass 1. Do you guys mind if I'll just use your initials? Mass 1 is student C, mass 2 is student D, and mass 3 equals student J. I should probably write it like this, mass, mass. And then I'll actually use the water bottles. And this will be the ones coming in. And then I'll say mass exit 1, mass exit 2, mass exit 3 equals the mass of, I'm just going to call it bottle 1 equals the mass of bottle 2 equals the mass of bottle 3. And we can assign numbers to it. So now we've kind of gotten through all the the sticky algebra, and I'm just gonna make some numbers up, and we'll do this in kilograms. I'm just gonna say 90, 91, 93, and let's just say the bottles equal 1, 2, and 3, and we'll just all these are in kilograms. So if we wanted to keep track of the mass flowing in and out of the room that we're in, we would just write it like this. Let me see if I can find some room here. Yeah, I'll just do it right above. So, and I'm going to rewrite this DMCV, and again, the control volume is just the volume of the room. As I said before, it could be wood growing in the forest, wood flowing out of the forest through the timber industry. It could be wood flowing into your chipper, and then chips flowing out. So, but let's just do it for us in the room here. So I'm going to rewrite the little d's as big D's, and it just means the change, the change in the mass in the control volume over the change in time. So we can just think of the time as starting at 10:30 a.m. when the class started, and then moving forward in time towards 11 when I pretended to throw the bottles out of the room. So from there we would just say this equals, and we know we had 3 masses coming in, and I guess I'll just go ahead and label them. I've got I think this one we called C. This one we called D. This one we called J. So those are the 3 masses coming in, and they were 90, 91, and 93. So equals 91 plus, or sorry, is it 90? Yeah. 90 plus 91 plus, that's how good my short-term memory is, man.
3.
3. Thanks. So 90, 91, 93. There we go. Minus. So this chunk right here, 90 plus 91 plus 93, is just this first summation. So the plus, like, where did the plus signs come from? Well, they came from that sigma, because that sigma just means addition. It just means summation. That's all it is. Minus the sum of the masses that exited. And I call the 3 masses that exited, again, here's bottle 1, here's bottle 2, and here's bottle 3, and I pretended to chuck all 3 of those right out of the classroom. And so from there, what did I say? Just 1, 2, and 3. So minus 1 plus 2 plus 3. So I've got those 2 guys. You can put parens around them. In fact, you have to put parens around that one because you've got the minus in front of the whole thing. So where did these plus signs come from between the 1, the 2, and the 3? Well, they came from that sigma. That's all it is. So, yeah.
It's not me.
Not an E, it's a sigma, yeah. And I don't know if we went through it, but if you get a chance, just go into Microsoft Word. This is how I deal with the Greek symbols. And I'll just type them out like this. So A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z.
I say this on the other one
Yeah,
where you did this.
yeah. I think I did it
Tuesday
for
night.
I did it for 214. And it's a good little skill. So if I take this guy, I can make the whole thing caps. I can copy it. Oops, no, not. I'll make the whole thing caps. I'll copy it, stick it down here, paste it, and if I turn that into a symbol, yeah, so right there, so T looks just like T. You know, T actually becomes what's called tau in the Greek alphabet. Right before it is S, and there it is, sigma. So, yeah, it kind of helps with the Latin to Greek translation, and the lowercase is just here.
So basically, somebody took something really simple and made a really hard formula out of it.
Yes and no. I think, and again, mathematics is just a language, and I guess it was the Arabs, 3,000 years ago, came up with algebra as a way, because I think before that, we could count and talk about numbers and all that, but then all of a sudden, if we just had one language that could take care of all types of arithmetic, let's call it algebra, and so you might say, gosh, it's really simple, or it's really complicated, but on the other hand,
Look at it at first.
yeah, yeah.
But then when it's all explained, it's like, if I put 50 pounds in and I only get 10 pounds out, that means there's still 40 pounds in there in that hour or whatever the time was.
Exactly.
I mean-
Exactly. And this is just another way to write it. Yeah. So hopefully that kind of tied in the symbols with an everyday.
The dots over the M's, what are those signals?
Oh yeah, I'll tell you exactly what the dots are here too. Yeah, we'll get to that. No, it's we'll go over it. No, it's definitely worth going over. So, and I'll just go ahead and finish this problem. So, 90 plus 91 plus 93 equals minus 6 equals 268. There we go. So, what we decided or determined or figured out, so equals 268 kilograms. So this is the change in mass over the change in time. The change in time, we just said that delta T equaled 30 minutes. So, the delta just lets you know that time changed. So delta, another way to write it is delta T equals 11 a.m. minus 10:30 a.m. equals 30 minutes. So now that delta, and if we go back to our Greek, there it is, right where it should be with the D. It just means change. Right there is 30 minutes. So we took that Greek symbol, that delta T that was in the denominator, and actually turned it into a number that we can all understand. 30 minutes, half an hour. Fine. Okay. Now, what's the dot mean? I'll show you exactly. So, and here's the beauty of calculus, if you will. So, I'm going to try to box this off that I did before. Glad I got to talk about Niagara Falls a little bit. Did you guys hear they're going to shut down Niagara Falls again? Something?
Yeah, I heard about that, the observation.
Yeah. I don't know all the details, but it's kind of wild.
That's weird.
Because what?
I didn't see that there was It was safety or?
I'm not sure.
It was.
I don't know if it's like they're going to redo the power system on it, or I don't know.
Should be jumpers.
Open it up for rock climbing.
Too much duct tape.
Okay, so what I'm trying to do here with this, these three little boxes, is sort of show, a continuous summation with the water, a discrete summation with the apples, a continuous summation with the integral sign, and normally what you would see here would be a little dt, and usually the t just means time, and the little d just means a small change in time. The big D means a big change, and so what we'll do right here is put. I'm going to put a delta down here because this means change or slicing. So this is this middle part. Let me write it down here. This middle part is adding. We already saw there's continuous addition, discrete addition. Over here, this also has to do with adding, but it's more, I'm just going to call it slicing. So there's one way to do it with the big delta. The other way is with, like I just showed, with the little d. But yet another way is just with the dot.
Okay.
So what the dot is telling me, and I'm just looking at one more little.
Change in mass.
Yeah. So m dot equals dm dt, and this is, I'm going to just sort of say equals-ish delta m delta t.
So the dot is essentially doing a rate of change, a change and a rate.
Yes.
Okay.
Yeah. The dot is just the rate of change with respect to time.
Perfect.
And so for example, and let's just do one little example with it. Let's say you were, and let's do a graph. I think that'll help. Let's just do a graph with it. Super easy, super simple. All right, let's say you're like, what do you guys want to do? Gain weight or lose weight?
Well, I'd like to lose it.
Let's lose some weight. We'll lose some weight.
What the weight is.
Well,
Fat
that's
enough.
right. Go to the gym. I want to gain some fat. Okay, but let's look at it this way. So here's time, and we usually think of time as the independent variable flowing off to infinity, and here is mass, or your weight. And so let's just say this is now, and I'll just call it, February 4th. And let's just say this is the future. This is going to be March 4th. Let's just say we got a goal of losing 5 pounds by March 4th, right? So we'll plot our mass right here. Let's just say you weigh like 205. Right? And let's do this in pounds.
Usually he's been watching my webcam.
And then we'll go down 1, 2, 3, 4, 5. So let's come over here. And this is going to be 200 pounds on March 4th. Okay, so right away we can tell that the change in mass is going to equal, and the way you have to do this, you have to start from the future and go back to now. So it's going to be 200 minus 205 equals 5 pounds. Yes. The change in time, delta t, equals March 4th minus February 4th equals 28 days. Okay, so we just used the big delta. Now, in between here, like so, throughout the day, I'm going to drink some water, I'm going to gain some weight. I'm going to go to the bathroom, and I'm going to lose some weight. I'm going to go sweat some sweat something off the gym, I'm going to lose some more weight. So we're always, gaining and losing mass depending on our own bioenergy. So, so it's going to be doing something like this, right? Woo, yeah, woo, whatever. Okay, but eventually, you're going to hit this. You're going to hit this goal. So why screw around with the little d's and the little dots and all that? Well, what they're allowing you to do is just you could look with a magnifying glass in on your mass as time changes. So if we just went in here, we could just take a little slice here, and I could call this, little dt, because my big dt is the full thing. This from here out to here, that's my big dt, right? And then from here to here is my big dm, or delta m. But all of these other little d's are going to eventually add up to the big D and the big M, the big T. So, so there's your little delta T, and then this guy, it's getting kind of small, but here, this little chunk here would be your DM. This dot is more or less, it's just the slope of this roller coaster. So right here at the peak where you were gaining weight, and then maybe you fell asleep and you got up, got to the bathroom, you lost a little weight, et cetera, you starved yourself all day long, and you just kept losing weight all day long. But right here, m dot at that peak equals 0. The slope is 0. The mass is not changing right there, right? Right here, m dot is less than 0 because you're losing weight. Right, right here, m dot is greater than 0. So m dot is just kind of like keeping track of that slope as you go.
So all the valleys equal 0 also.
Fantastic, fantastic, good, perfect, absolutely.
This
Yes.
is where you had the flu.
There's where you had the.
Kind of what the Republicans do in accordance with climate change. They just take a slice instead of looking at the whole change.
Yeah, you can cherry pick your data, exactly.
I can't get in on that.
That's all right.
We won't say Republicans. We say the non-climate change.
Yeah. I was with an oil geologist, and he's like, the ice age is going to come back. Like, we might hold it off by burning some fossil fuels, but like, it will come back. The ice will return. So.
Was it New York? 27 inches?
Not going to be happy, but anyway. So does that make sense? What the dots mean and the D's and the delta? They're all related.
Forget my next week.
Well, no, that's why I'm YouTubing this. We're going to have to.
That is why I like this, because you can go back.
Yeah. And hopefully my handwriting's kind of neat enough here. So I think what we've done, we've really knocked out equation 2.1. And we were talking about this earlier. Like, man, I was sick that day in 8th grade algebra when they were doing adding equations, and I never got it. And so knowing this equation 2.1 is pretty critical. Not that we're going to be using the summation notation all the time, but when I say, m dot, you're gonna remember. You're like, oh, my weight was increasing. It was positive. It was either in a valley or a peak. So I'm glad you said that, Cody. That was fantastic. So that's mass balance. That's all it is. It's just mass accounting.
10 minutes of our time being stupid.
No. No, seriously. I don't know. I don't know where this brave new world of education is going, but I think. Like YouTube is going to get smarter.
Boy.
You're just gonna talk in your handheld and say, Siri, what's m dot? And I've already gone into my own YouTube lectures, and they're being voice to texted. Just like you see on CNN. Because we have to do that for the ADA Act, Americans with Disabilities. So, but YouTube's doing it for us. There's artificial intelligence turning my language into written words, and it could be then, every time I say MDOT, some little program is saying, did the way Leighton explained it, is that going to make sense? Is this going to become how, or, because there's the Khan Academy guys out there doing it, there's other professors doing the same thing, so hopefully us faculty members will work ourselves out of a job, and we'll just
Well, the
check the box, man.
interesting thing is they'll develop an algorithm that's custom suited to you, so it's like, did he mean the physics term?
Oh.
Or did he mean the letter?
Yeah. Yeah.
They'll know because of what your history is.
Oh, yeah.
Yeah, I mean, if you do that now, like you voice to text your Google
Yeah.
on your phone, like I can say something in there that's totally esoteric, like, unique to me.
Right.
Google will be like, oh yeah, I know what you're searching.
Wow.
Yeah, but if somebody else searched that same thing, Google will be like, I don't know what you mean. It's spooky.
It's getting spooky. Yeah, it's coming.
I haven't got into talking to my phone yet, so.
I don't either. And I still
My
talk
car
about
ever
that.
does